Let's talk about linear approximation and differentials. First, we look at a motivating example. Suppose we want to find the square root of 101. Well, this is not obvious, but let's just find its approximate value, and with the help of derivative. Well, everybody knows what square root of 100 is. That is equal to 10. So square root of 101 should be close to 10, but not quite equal to 10. All right. Let's recall when we defined the derivative, we used the tangent line as a motivation. And here is the picture. The point, we're looking at tangent line at this point. X equals x, x equals a, and y is automatically equal to fa. Okay, here is the picture of the tangent line. And this line should be is a good approximation for the function fx, at least when x is close to a. Okay, so that is the idea for linear approximation. Let's look at, so starting with a, let's look at the point x equals x, and y will be fx. All right, so y equals fx will be the point on the curve. But let's find out the point on the straight line. So that is basically you work out linear line, the equation of the line, and then you can determine the y value. But you can actually just kind of see that. Basically, you start with the height fa, and then you want to know how much y increase from fa. Well, you draw a right triangle here, so it should be this side, okay, up to the straight line, and that side should be equal to delta x, how much x increases, times the slope, and we know slope is a derivative. So anyway, this gives you the following formula. This is exactly what I was talking about. So fx up here is approximately equal to fa here plus the slope f prime a times x minus a, which is how much x increases. And this is called a linear approximation. Okay. Now let's see how exactly this works. Let's using this example. First, you have to decide what fx is. Well, that is obviously just the square root of x. So you use square root as your function. And x is equal to 101, so you can compute the square root of 101. And a, we choose 100 to be a, because that's a very simple point for which you can compute fa and f prime a. All right, let's compute this. Fa is just equal to 10, as we said. To compute f prime a, you need to compute f prime x. Well, square root is the same as x to the 1/2 power, and then you apply power rule. Basically, you move 1/2 to the front, and you subtract 1/2 by 1, so you get a negative 1/2. So this is the derivative at a. Now a is 100, so it's equal to this. And then you work this out. It's pretty easy to do it. 100 to the negative power, you flip that to the bottom. Basically, 1/2 power is a square root. Square root of 100 is 10, so it's 20 on the bottom. And that is 0.05. Now to compute the original question, to compute the square root of 101, we use this formula here. So it's approximately fa, 10, plus f prime a, 0.05, times 1. Where did we get the 1? That is equal to x minus a. Basically, it's how much x increases. All right, and that is equal to 10.05. Okay. Here is an exercise that you can do. It's pretty straight. I mean, it's really the same idea. You can just do it sometime when you yeah, if you want to just make sure you know the method. Okay. All right. Let's follow the idea we just learned. Remember this expression is the approximate value for fx when x is close to a. And because of that, we denote this by function Lx. Basically, this is the straight line function that we have. It's this straight line equation. Okay. All right, this function is called the linearization of f at a. Basically, you have a curve, but you use this linear line to approximate our curve. And then our formula that we had before becomes f of x is approximately equal to Lx, which is this. Okay, I'm talking about the formula in right here. Okay, so the right hand side we denote by Lx, and fx is approximately equal to Lx. Okay, which is this. Let's look at another example. Find the linearization of this function 60 over x at a equals to 60. And then use this to approximate f61. Okay. Well, we just use the definition of linearization. Remember, it is fa plus f prime a times x minus a. Okay, and a is 60. So you compute fa, 60 over 60, that is equal to 1. F prime a, you compute the derivative. This is just x to the negative 1 power, and then use the power rule. That's how you get minus sign over here. And then you have a minus 2 power, which is square on the bottom. All right, a is equal to 60. So you have 60 squared, and cancel out a 60 here, you still have a 60 here. Okay, so that's f prime a. And then to come to that, you can just write down what the linearization is. It's fa plus f prime a times x minus a, right? Fa is 1, f prime a is this, okay? And then x minus a. And you can simplify this slightly by multiplying this into the parentheses. 60 and 60 cancel, so that is actually equal to 1 because the minus and the minus also cancel. 1 plus 1 is 2. So it's this. So that is the linearization of our function. Okay, if you want to use this idea to find the f61, you just put x equal to 61. So what do you get? Well, it's equal to L60, approximately equal to L61, which is you put 61 into here, and then plus 2. And that works out to be 59 over 60. Let's see, yeah, so 2 is 120 over 60, and then 120 minus 61 is 59, okay? All right, so that is the approximate value for f61. Well, you may say, this is nonsense. This is this is another fraction, and this is a fraction as well. So you just start with a fraction and get, which is 60 over 61. You say that number is approximately 59 over 60. So what are we doing here? You know, this doesn't really simplify. We just look at this example to see how it works. But more importantly, this actually has a good physical interpretation, and then you will see this is easier, much easier than that one. Okay. Suppose you're driving on a highway, and from A to B, the distance from A to B is 60 miles, and your speed is 60 miles per hour, therefore 1 mile per minute. Okay, and now if you increase the speed to 61 miles per hour, and then naturally you will arrive a little bit earlier. The question is, how much time will you spend this time? How many minutes will you arrive? Okay. Well, so by the computation here, you see the time is really 60 over the distance over the speed. Distance is 60. Speed was 60 before, and now it's 61. So we're really talking about f61. Okay. By the previous result is approximately this number. Okay. So it's that much of hours. And if you ask how many minutes, how do you do that? You just multiply by 60. Look, 60 cancel with 60, so you get 59 minutes. So this basically means that if you increase the speed by 1 mile per hour, if you increase by that much, then your time will shrink by a minute. That kind of makes sense because you're driving at 1 mile per minute. Okay. This is when your speed is close to 60. When your speed is far away, suppose you drive like 90 miles per hour, you cannot use this approximation. Okay. One quick question for you. You can think about the actual time that you spend. Should it be close to 50? Because this is approximate value, 59. Close to 59 minutes. But is it bigger than 59 or is it less than 59 minutes? I leave it to you to think about this. Let's look at the differential. We start with the same formula at the very beginning. And let's change the notation a little bit. Instead of a, let's call this x. Okay. And now that means we cannot call this x because x is already used here. Remember, this is just a plus a little bit and increase a little bit. And we denote that a little bit by delta x. So this becomes x plus delta x. And then x minus a is how much you increase, which is exactly delta x, and a becomes x. So this formula becomes this one. Now if you move fx to the left, it becomes a negative. We got this. What is this? This is how much f increases, right? Because this is the final value minus the beginning value. And we also denote this by delta y. And this says how much y increase, delta y is just equal to f prime x times delta x. Okay. Or this is roughly, this says delta y is roughly dy. And what is dy? First of all, delta y, as I said, is how much y changes. It's the actual change. Dy by this is just a notation, so it denotes f prime times delta x. It denotes exactly the right hand side. Okay. Now delta x is often denoted by dx. That's a notation that Leibniz created. It turns out to be very convenient to use. It kind of makes sense because if you use delta x equal to f prime times dx, f prime would be 1, so delta x should be equal to dx. Anyway, this is the approximate change. So we have delta y is approximately equal to dy. and dy is called a differential. Let's look at one more example. Oh, by the way, this is the picture. This is the picture, the nice picture that yeah, let's see. This is the original point, x equals x, and then increase by delta x. So this much is delta x. And also we denote that by dx. So this becomes, the x value becomes x plus delta x. Okay, and let's look at how much y changes. From here to the top, to the tangent line is dy, is this one, is the approximate how much y changes. And then from here to the curve is delta y, which is the actual change. And we're saying that delta y, this is approximately equal to dy. Okay. We have our final example. Okay, let's see. We have a sphere with radius to be measured, and we measured that and we find out it is 21 centimeters. Now, there's always error, but we can have control. Suppose we know the error of our measurement is at most 0.05 centimeter. It means the radius could be 21 plus up to 0.05, or 21 minus up to 0.05. So it's within that range. Now, because of the error on radius, you will have error on the volume of the sphere. And we want to compute maximum error in using this measurement when you use that to compute the volume of the sphere. Okay? In other words, what's the worst scenario? You know, your answer could be away from the actual volume. Okay. Well, first of all, let's recall the formula for volume. If you denote V by volume, then volume is just this. That's a well-known formula where R is the radius. Basically, we want to calculate how much error are there for V. That is really just the delta V. Okay. And we can use a differential dV. Delta V is approximately dV. dV is f prime times dr. R is the variable here. And for f prime, remember pi is a constant. It's 3.14 something. So you should keep it here. R to the third is the only for the part for which you want to take derivative. So by the power rule, it's 3r squared. Okay. And 3 and 3 cancel each other, so you have 4 pi r squared here. By the way, this expression, as you might know, is area of the sphere. And this is not by coincidence. If you take the derivative of volume, you should get the area of the sphere. All right, so it's equal to this. And now we just enter all the data into here. R is 21, dr is 0.05, so we get this. And that, if you compute, is roughly 277. And the unit should be cm cube, because we're talking about volume. That's all.